Hello, today in this video I'm going to be explaining the relationship between air pressure and temperature as we are going up in altitude in an isentropic atmosphere. And I'm going to be using an ideal gas at a specific volume. So to begin, I want to start with the basic equation of statics. So the change in pressure over change in our altitude is going to equal our density times acceleration due to gravity. And I'm going to use up as positive, so our acceleration due to gravity is going to be negative. Now, to begin, I want to get pressure and temperature into my equation. And working with an ideal gas, we can use the ideal gas law. PV equals nRT. And we can rewrite density as mass over volume. And then that can be rewritten as our volume is going to equal RT over P. Since we're working at a specific volume and only 1 mole, N equals 1. So we can just leave it out of the equation because it doesn't affect it. And our mass will equal just the molecular weight of our gas in kilograms per mole. So using that, we can rewrite our equation as dP over dZ is going to equal negative PmG over RT. And now our next thing we want to do is we want to get temperature as a function of pressure. So the first thing, we're going to rearrange our equation and get pressure and temperature on the left side and put our dz on the other side so we can integrate both sides. So we get T over P dP equals negative mg over r dz. Now that we have this, we want to get temperature as a function of pressure so we can plug it into here and integrate the side. So to do that, we want to look, since it's an isentropic system, we know it is both reversible and it's adiabatic. And if it is adiabatic, then we know that in our internal heat equation, we know that du, our change in internal heat, is in the change of the heat, which is 0 for it being adiabatic, and that's going to be minus our change in work. And since it's a reversible process, our change in work can be written as P dV, because we're changing it so slowly, so the pressure is at equilibrium. And also for an ideal gas, we know that our change in internal energy is equal to the specific heat times the change in temperature. So we can rewrite as CV dt equals negative P dV. Now we need to get our temperature and volume back into the equation so we can integrate with the dt dV. So again, using ideal gas law, we can rewrite as CV dt equals negative RT V over V dV. Now let's just rearrange again to integrate both sides. CV over T dt equals negative R over V dV. Take the integral from T1 to T, so from our starting temperature, T1, to whatever our final temperature is of T. Same thing with V, V1 to V, and we get CV times the natural log of T over T1 equals negative R times the natural log of V over V1. And then at this point, we once again just need to continue rearranging our equation to get T as a function of P, our temperature as a function of pressure. So we can do T over T1 equals V over V1 to the negative R over CV. And then bringing pressure back into our equation, we get T over T1 equals T over P over T1 P1, still to the negative R CV. Just continuing to rearrange, we get T over T1 is going to equal T over T1 times P over P1. No, P1 over P, my bad. P1 over P to the negative R CV, and we get T over T1 to the R over CV plus 1. That's going to equal P over P1 to the RCV. So now we rearranged it, and we have our temperatures on one side and our pressures on the other side, but we want this T, our final temperature, to be the function of pressure, because T1 and P1 are both constants because they're our starting temperature and pressure. But before I do that, I'm going to look at these exponents, and this one can be rewritten as R plus CV over CV. And we know in an ideal gas that R plus CV is equal to CP. So that's our specific heats. So this can be rewritten as CP over CV, which I'm going to label as K, our ratio of specific heats, may also be seen as gamma. And then we can also rewrite this one as R equals CP minus CV. So it is CP minus CV over CV, so we get K minus 1. So I have T over T1 to the K equals P over P1 to the K minus 1. Now I just want to rearrange and get T by itself. So T is going to equal T1 times P over P1 to the K minus 1 over K. Now I have T as a function of P. So I can plug it back into our original equation and I can get the integral of both sides. So our original equation of T over P dP equals negative mg over r dz. And then I can now plug this T in for this T. So I get T1 times P over P1 to the K minus 1 over K. All that over P times dP, and that's going to equal negative mg over r dz. Now I just take the integrals, and like I said before, our T1 and P1 are constants because they're our starting temperature and pressure, so they can come out of the integral. So T1 P1 to the 1 minus K over K is going to be equal to P to the K minus 1 over K minus 1. And we're going to go from P1 to P2. And then that's going to equal minus mg delta z over r. So that's obviously a simple integral. This one is a little bit more complex, but still not bad. I'm gonna go ahead and just continue. I'm gonna move my temperature, my T1 and P1 over to that side. P1, P2, K, -1 over K, -1. That's kind of hard to see that that's an exponent, but, and then that is going to equal wait, what am I doing? P1 to the K -1 over K times negative times M G delta Z over RT1. And then I can take the integral of this, which comes out to being P to the K -1 over K over K -1 over K. That's going to equal that. And then I can move my multiply by K -1. So I get this equals negative. Oh, I completely, hold on that. I did not even, all right, I didn't evaluate the integral, I just integrated it. So P K -1 over K over K -1 over K, evaluated from P1 to P2. So I get P2 to the K -1 over K over K -1 over K minus P1 to the K -1 over K. And then I'm going to move my K -1 over to the other side. So this is going to equal K over K -1 times P1 K -1 over K times M G delta Z over RT1. Now I'm going to move my P1 over to that side. So plus P1 K -1 over K. And now I can just factor out the P1 K -1 over K. So I get P2 to the K -1 over K is going to equal P1 K -1 over K times 1 plus, this is a negative, plus K over K -1 times M G over R D1 delta Z. And then to finish it off, I can just move my, dang, one line of room. Now I gotta, that's all I miss. Gotta erase all this now just to put this last line in. Now I can finally rearrange my equation to solve just for P2. So P2 is going to equal P1 times 1 plus K over K -1 times M negative P1 mg delta Z over R T1 all raised to the K over K -1. And that is our final equation relating our pressure and our temperature and our isentropic atmospheric equation.